Object goal navigation in unseen environments is a fundamental task for embodied AI. Agents in existing works learn the policies based on 2D maps, scene graphs, or image sequences. In this work, we propose a 3D-Aware object goal navigation framework to utilize the rich information contained in 3D data to boost the performance, while maintaining the sample efficiency and computational cost acceptable. We designed two sub-policies, namely Corner-Guided Exploration Policy and Category-Aware Identification Policy, to simultaneously perform by taking in online fused 3D points as observation. Through extensive experiments, we show that this framework can dramatically improve the performance in object goal navigation. Our framework achieves the best performance among all modular-based methods on the Matterport 3D and Gibson datasets, while requiring less computational cost for training. Considering the object goal navigation task happens in 3D space, a 3D-aware agent can advance its capability via learning from fine-grained spatial information. However, leveraging 3D scene representation can be prohibitively unpractical for policy learning in this floor-level task, due to low sample efficiency and expensive computational cost. To tackle these challenges, we propose a novel framework composed of an online semantic point fusion module for 3D semantic scene mapping and two parallel policy networks in charge of scene exploration and object identification, along with a local path planning module. Our contributions include: we present the first 3D-aware framework for object goal navigation task. We build an online point-based construction and fusion algorithm for efficient and comprehensive understanding of floor-level 3D scene representation. We propose a simultaneous two-policy mechanism which mitigates the problem of low sample efficiency in 3D-aware object NAV policy learning. Our pipeline is as follows. The online semantic point fusion module extends a highly efficient online point construction algorithm to enable online semantic fusion and spatial semantic consistency computation from captured RGBD sequences. This 3D scene construction empowers a comprehensive 3D scene understanding for object goal navigation. Moreover, to ease the learning of navigation policy, we further propose to factorize the navigation policy into two sub-policies, namely exploration and identification. More specifically, we propose a corner-guided exploration policy which learns to predict a long-term discrete goal at one of the four corners of the bounding box of the scene. These corner goals efficiently drive the agent to perceive the surroundings and explore regions where the target object is possibly settled. And for identification, a category-aware identification policy is proposed to dynamically learn a discrete confidence threshold to identify the semantic predictions for each category. In the end, the input for the local path planning module will switch between these two goals, depending on whether there exists an identified target object. In Matterport 3D and Gibson, our method achieves SOTA performance among all modular-based methods, while requiring less training time. And extensive experiments show the effectiveness of different modules in our framework. Next, we will provide more demos and analysis. First, we will demonstrate how efficiently our proposed corner-guided exploration policy works to navigate the agent. Then we will analyze one specific episode in detail to illustrate our agent's performance, especially about the identification policy. In the end, we will provide more demos. Prior works use the predicted continuous goals for exploration, under which we observe the so-called back-and-forth pacing or wandering for quite a lot of times. In comparison, our proposed corner-guided exploration could boost the exploration efficiency, while taking advantage of the semantic priors of the environment. Here, both of the exploration policies have been trained for the same 48 GPU hours. This is an episode of Looking for a Bed. As soon as the agent started, it was encountered with a deceptive object. It is actually a sofa, but sometimes can be detected as a bed. Here our agent mistook part of the sofa as bed, as shown by the red points. As the result, our agent set the sofa as our target object and continued to observe and approach it. Through constant identification and point-based fusion, the mistake was dismissed. Even if several points were still detected as bed in red, they were no longer consistent enough to be identified as a bed. Here we display the sequence of the structured 3D points across observations. We can see that the mistaken predictions were gradually improved through 3D point-based fusion. As a result, our agent gradually cancelled the predicted target goal. Then it switched back to use the corner goal for further exploration. After that, our agent continued to explore the environment and finally discovered the correct object goal. As it approaches to the real bed, its semantic prediction keeps confident and consistent, and the object passed through the identification policy in each frame. To sum up, our identification policy plays an important role in dealing with deceptive objects, and our point-based fusion algorithm offers more confident and consistent semantic predictions. Next we will show you more demos. Guided by the predicted corner goals, our agent can explore the environment both efficiently and effectively. The identification policy runs in parallel to leave out the false positive deceptive goals and to identify the true object goals. Thank you for watching this video.